I hear trumpet music in the background.
Trombone, actually.
Oh, trombone.
Yeah, J.J. Johnson. Okay, so welcome to Zhao. There he is. Have I pronounced that correctly this time?
Well, not quite there yet, but I appreciate your efforts. I'm used to that. It's
Okay. Do you want to say something and tell us who you are, where you're from, and so on?
Yes, so I am João Faria Martins. I am Portuguese, but I've been in the UK for nearly 4 years. And I used to do knot theory throughout my PhD. Then I went away from knot theory for a long time, and I actually been back to it in the last few years. And at the moment, I'm in the University of Leeds, which is quite a nice place. Yorkshire is a beautiful place as well, which I quite recommend. Right, so maybe I could start with the talk today. I just need to share my screen. Sorry, there's something that is not quite right here. Sorry, just need to, my apologies, I thought they had everything ready to start speaking.
There should be a little green thing at the bottom.
Yes, I found it now. Oh, because Zoom has this thing that you sometimes you have something open and Zoom doesn't detect you have it open. But now it's here. So I'm going to share my screen, and this is the title of my talk. Let me just try to. Sorry. Right, so cross modules are multiple two types, noticers and welded links. So as I was hinting when I started chatting to you guys, most of what I'm going to speak about today is actually something I've done quite a long time ago. It was in my first postdoc, so well over 2 years ago. And I've recently gone back to thinking about these things, partially due to this legal home grant, which is active, and I should probably mention it legally, which is this grant emergent fees from lattice model of higher gauge theory, which will actually supports some of the research I'm going to speak about in the end. Okay, and just to make sure, also to make sure I don't forget mentioning other people's work, which I probably should, let me mention other references on homotopy work. So foremost, this paper of Le Monaco, how to compute the algebraic two-type complement of surface. This beautiful paper by Susiu.
Jean, you've muted yourself as well as us.
Oh, it should have been unmuted.
I don't know what I've done. Right.
It's okay, we can hear you.
Can you hear me? So the main reference to
fine.
this talk is this paper, The Fundamental Cross Model Complement of the Knotted Surface. And also so that I don't forget citing references, which I'm going to use quite a lot. So the references on combinatorial homotopy, which I'll use a lot of times throughout this talk, is this book by Brown, Higgins, and Siviero, Nolabin Algebraic Topology. These two books by Bowers, Combinatorial Homotopy in Four-Dimensional Complexes, and Algebraic Homotopy. And most of the combinatorial homotopy which I'll use today is actually in this very old paper by Whitehead, Combinatorial Homotopy 1 and 2, which was the paper where Whitehead defined CW complexes, which were actually defined to do combinatorial homotopy. And let me also mention this paper by Baez and Lauda, which is quite well written and influenced this talk quite a lot as well. Right, so let's start the talk. So one thing that everyone knows when they start doing knot theory is the fact that knot complements are spherical. So let K be a one-component piecewise linear smooth knot in S3. And Papa-Kyriakopoulos theorem says that S3 set minus K is in a spherical space. And by the way, being a spherical means that the homotopy group pi I of S3 set minus k is 0 if I is greater or equal than 2. And more generally, S3 set minus L is always in a spherical space if L is a non-splittable link. For example, something like the Hopf link, which has like indeed two components, but you cannot separate them into two parts without breaking the components. Right, so first definition for today's talk is the definition of an n-type. So let n be a non-negative integer. An n-type is a path-connected point space, x star, satisfying two very simple conditions. First condition is that x is homeomorphic to a CW complex with star being a zero cell. And let me just say that this condition is frequently omitted in models category literature because normally model categories don't really mind about formally inverting weak homotopy equivalences, but probably all do mind about formally inverting weak homotopy equivalences. So let's just work with CW complexes. And the second condition is that the pi I of x, the if homotopy group, is 0 if I equal than n. And I'm also going to consider the category n-types, which is the category of objects, the n-types, and given to n-types x and y, morphism from x to y are pointed homotopy classes of pointed maps. I'm actually wondering if you could see the very bottom of my screen. Can you actually see it?
No.
Oh,
No.
that's a shame. That's a shame. Yes, I just noticed now.
Yes.
So I don't know
Ah.
how to.
Oh yeah, it keeps going on and off.
Yes, my apologies for that.
Yeah.
Always learning. So, so a consequence of Papert-Kirkoros's theorem is that the complements of non-splittable links in S3 are one-types. So, i.e., there are spherical spaces, and there's this well-known theorem saying that the fundamental group functor pi1 from one-types to groups is an equivalence of categories. And essentially, this implies two things everyone knows. So, two one-types, i.e., a spherical spaces x and y are homotopy, and the fundamental groups are isomorphic, and maps f and f prime between one type.
Rog, mute your microphone. You keep cutting in.
Yes, and maps between one types are pointed homotopic if and only if the induced maps at the level of pi1 are equal. And in particular, if you combine this with the sphericity of knot complements, we have that the homotopy type of the complement of a non-splittable link in S3 is classified by its fundamental group. And before I go on to cross modules and knotted surfaces, let me just remind everyone about the vertical presentation of the complement of a knot. So if you have a knot projection, you can easily find the presentation of the knot group by generators and relations. We have a generator for each arc of the projection and a relation at each crossing. And my apologies, you cannot see the bottom, something I just noticed today. Right, so let's go to the main topic of this talk. Let's think about complements of knotted surfaces sigma in S4, and we need to go beyond one types. So let sigma in S4 be a closed surface smoothly embedded in S4. So any genus, any number of components, possibly non-orientable, there's no restrictions here. And the fact is that S4 set minus sigma need not be spherical. In fact, I suspect it never is. And also the fundamental group of the complement of the knotted surface doesn't necessarily classify the complement up to homotopy. So in order to classify the complement of the knotted surface up to homotopy, you must look at higher order homotopy type information, i.e. something beyond the fundamental group of the complement. And today we're going to look at one space which is called the homotopy 2 type of the complement of the knotted surface. And let's call it P2 of S4 set minus sigma. And let me just say this, that this topological space, P2 of S4 set minus sigma, is obtained from S2 set minus sigma by functorily killing all homotopy groups by I for I greater or equal than 3. In other words, I want to throw away all homotopy theoretical information of order greater than or equal to 3. So in particular, P2 of S4 set minus sigma is a 2 type. By the way, P2, so P goes for Ploshnikov. It's also called the second Ploshnikov section. And theorem, the category of two types is equivalent to the homotopy category of two groups. That's where the higher algebraic information will appear, to be explained later. And we're going to see two groups as being represented by crossed modules. So what is this thing of a cross module? So definition cross module. So a cross module is given by several little things. So we have a map partial from E to G, where E and G are groups. So in particular, we have a group map, i.e. a homomorphism partial from E to G. And the nomenclature, usual nomenclature is that G is called the base group and E is called the principal group. And you also have an action of G on E by automorphisms. And two very sensible conditions must be satisfied, which are called the Pfeiffer relations, which I probably should just display. So the boundary of G acting on E is equal to G boundary of E, G minus 1. And boundary of E acting on on F is just F conjugated by E. Okay, right, so example of a cross module. So the simplest example, G can be a group, A can be any abelian group. We can consider an action of G on A by automorphisms, and we immediately have a crossed module where the boundary map is trivial, meaning that it sends everything to the identity of G. Okay. So another type of example, which is going to appear quite frequently in today's talk, is that we can just grab A and G abelian groups and consider any map from A to G, so map meaning a group homomorphism, and you can just consider the trivial action of G on A. And this is another example of a cross module. It's actually quite frequent in today's talk. Okay, so two examples of cross module, a group acting by automorphisms on an abelian group. The partial is trivial, or consider any map of abelian groups and the trivial action of the group G on the group A, and like this you obtain also cross module. Okay, right, so let me just give some more examples of cross modules. So if you grab any group H, you can put G to be the automorphism group of H, and you consider this map AD that sends H to the automorphism group of H. Essentially, it sends a group element to the inner automorphism it defines, and then this defines a cross module. And I think this is enough algebraic examples. Let's go to topological examples. So if you look at a pair of spaces, M and star, we immediately have a cross module, which I'm going to call big pi 2 of M and star, which is defined by considering the boundary map from the relative homotopy group to pi 1 of M star, and considering the usual action of pi 1 on pi 2, then in the relative case. This is actually the original example of cross modules that appears, I think, probably the original paper of Whitehead on combinatorial homotopy was one of the first places this notion appeared, but I might actually be wrong about this thing. Right, so an example of these fundamental cross modules, let's just see what it is for D2S1. So what is pi 2 of D2S1? So here is the two disk. Boundary is S1, so what is the fundamental cross module of it is quite clearly just given by the identity map from Z into Z and the trivial action on Z on Z. This just follows from the homotopy exact sequence of the pair D2S1. Okay, so these things are actually computable and not too hard to compute. Right, so I said that in order to use cross modules to compute higher dimensional homotopy, you need to develop your theory a bit more. So we should probably speak a bit about free cross modules. And groups are free on sets, but cross modules are free on something slightly different. So let V be a set, G is be a group, and let's consider a set map, which I'm going to call partial 0 from V into G. And this is the data that lets us define a free cross module. Okay, so think of it. Groups are free on sets, cross modules are free on sets, mapping to groups. And by the way, my notation for free cross modules is this one, U of partial 0 from V into G. And it has, because it's a free cross module, several components. First of all, we have its principal group, which I'm going to denote this way. So F of V mapping to G. And by the way, the base group is always G for other reasons, and there's an action. And universal property is essentially the only thing it can be. So I have this map V, I have this map partial 0 from V into G. I can upgrade it into a cross module where V includes, and okay, universal property given any cross module E mapping to H, and any homomorphism from here, any homomorphism from here to here, any set map from here to here that makes it commute, gives rise to unique map from here to here that, well, makes the diagram commute, and moreover gives rise to a homomorphism of cross modules. Everything fits in quite well. And by the way, the construction of this object here is also not that complicated. It's almost like a free module, a free G module with base V, but then you need to impose the second Pfeiffer condition, but things can be done. They're really not too hard. Right, so let's speak about one beautiful theorem of Whitehead's, quite an old one. And let's consider a space X, and let's attach cells to it. So for example, here I have a space, it's genus 2 surface. Let's consider two cells, C1 and C2. Let this cell attach along this path here. Let this cell attach along this path here. So, and let's Y be the space you obtain by attaching cells C1 and C2 to X. So Whitehead theorem says that if Y is obtained from X by attaching two cells, then the fundamental cross module of Y relative to X is free on the attaching maps of the two cells. It's a bit of a cross module version of the relative Hurwitz theorem. I think it's relatively well known. Okay. Right, so this means that this fundamental cross modules of pairs, at least, yes.
Excuse me, what do you mean by free on the attaching maps?
So if you go upstairs, so if you have a set and a group, we can always consider the free cross module. So if you have any set mapping,
oh, I see. Thank you. Yes.
It's free on the attaching map to two cells. It's quite simple. I mean,
yes, beautiful.
It's beautiful, but a lot of, well, Whitehead's work is beautiful, though it's very hard to understand what he writes. Right. Absolutely. So this is Whitehead's theorem, which actually underpins all of this construction. Right. So let me just speak about some facts about cross modules. Hinted, so cross modules and their maps form a category, and each cross module, here E partial mapping to G embeds in an exact sequence. Well, just convert a map into exact sequence in the obvious way. Consider the kernel of partial and the co-kernel of partial. So we call the kernel pi2 of G and the co-kernel pi1 of G. And they also yield always a cohomology class, omega, which lives in H3 of pi1 of G, pi2 of G. In fact, well, every cohomology class in H3 can be represented by a cross module. It's a well-known fact, again, quite old. And let me speak about just another notion, even to bridge what I'm speaking today with Samuel Lomonaco-Stokes, is the notion of an algebraic two-type, which is actually a triple AKW, where A is an abelian group with a left action of K and omega a cohomology class in H3 of Ka. And let's recall that we have a algebraic two-type functor from the category of pointed topological space to algebraic two types, and it sends a space X to a triple, so pi2 of X, pi1 of X, the K invariant, and this is called the algebraic two type of X. And we analogously have a functor that sends cross modules to algebraic two types, so it's the same type of story. So, but let me just say that a classical result says that the algebraic two type of a space is so the algebraic type of a space determines the homotopy type, but non-pointed homotopic maps between two types may induce the same map on fundamental algebraic types. So in a sense, cross mods are slightly better than triples pi2, pi1, k of x, but that's my opinion, but I mean, other people may have other opinions. Right, so let me quickly speak about homotopy of cross modules. So a cross module in particular contains a short complex, E mapping to G, and given two cross module, G and G prime, we have a notion of homotopy between maps from G to G prime. I'm speaking about cross module maps. And because G and E prime need not be abelian groups, homotopies are not built on group homomorphisms, they're rather built on group derivations. And in fact, I can form a certain category, which I'm going to call COF cross modules over Kong. I'll explain the notation in a bit. So the objects are cross modules, partial from E to F, where F is a free group, and maps from G to G prime are homotopy classes of maps from G to G prime. By the way, COF means cofibrant, so these are cofibrant cross modules because there exists like an underpinning model structure in the category of cross module where the cofibrant cross modules are exactly the ones such that the base group is free. Right, so the theorem underpinning this discussion, the homotopy category of cross modules is equivalent to the homotopy category of two types. And a more concrete way to say this thing is that the category cross modules over Kong, so cofibrant cross modules up to homotopy, is equivalent to the category of two types. So look at the top one as like the model category theoretical way to say the homotopy category of cross modules is equivalent to the category of two types. The bottom way is a bit more concrete way of saying so. Look at the cofibrant cross modules, consider homotopy maps between them up to homotopy, then and what you obtain is equivalent to the category of two types. And again, this is oh, I thought I was going to say something else. End of the slide. So, and as I said, so Hegel of cross modules is equivalent to the category of two types. And let me say that this equivalence of categories can be made a bit more concrete. So, especially in the case of CW complexes. So, given a reduced CW complex X, we can consider its one skeleton as X1. And given that we have a pair of space, you can consider its fundamental cross module, so pi2 of X, X1. So, given by the boundary map from pi2 of X, X1 to pi1 of X1 with the usual action. And we can consider this category CW complexes over Kong, the category with objects reduced CW complexes with a chosen CW decomposition because you need to take these fundamental cross modules. And maps from X to Y are just pointed homotopy class of pointed maps. And well, we have a functor pi2, CW complexes over Kong to cofibrant cross modules over Kong. And there's this beautiful theorem of Whitehead and MacLean from the 1950s, which says exactly that when restricted to the category of two types, then pi2 is an equivalence of categories. And in particular, this fundamental cross module, pi2 of X, X1, is faithfully representing the homotopy two type of X. And in particular, this fundamental cross module of the pair X, X1 determines pi2 of the space, pi1 of the space, and also the k invariant, which is actually the last line of the slide, but I'm afraid you won't see. Okay, my apologies for the slides. Right, so, and that says that if you compute the fundamental cross module of the CW complex relative to its one skeleton, you actually know all of the homotopy two type information. So let me just say something else. So, second of all, these fundamental cross modules of the CW complex relative to the one skeleton are easy to compute. So if X is a reduced CW complex, let Xi be the union of the cells of index less than or equal to I. So there is a procedure to describe a presentation of the fundamental cross module of X relative to X1 by generators and relations. And of course, this needs to be in the world of cross modules. So the fundamental group of X1 is, of course, the free group on the one cells, because, well, X1 is just a bouquet of circles. This is a reduced CW complex. And if you want to compute the fundamental cross module of X2 relative to X1 by Whitehead theorem, this is simply the free cross module on the attaching maps of the two cells, as I explained a few slides above. And so pi1 of X1 is easy to compute. Pi2 of X1, pi2 of X2 X1 is just the free cross module. And now we should just try to figure out how to compute pi2 of X3 X1 in terms of pi2 of X2 X1. And this is a bit like when you want to compute the fundamental group of a space, you consider one relation, one generator for each one cell and one relation for each two cell. And because I'm speaking about fundamental cross modules, the relations are moved one step further. So pi2 of X1 is obtained from the fundamental cross module pi2 of X2 X1 by imposing a cross module 2 relation for each 3 cell. So maybe the catch sentence is this one. So the fundamental cross module of a CW complex X relative to the one skeleton has the following presentation. So you consider the free cross module on the attaching maps of the 2 cells, and you consider one relation for each 3 cell. It's really as simple as this, and none of the algebraic structures which I'm speaking about is so complicated that this would be like a really hard thing to understand. Maybe it's just some examples just to keep things simpler. Simple. I hope the example is not too simple. So let's just do a presentation of pi2 of D3 S1 by generators and relations. So D3 is a 3-ball, S1 is just the equator. So let's consider like this very obvious CW decomposition. So one cell, 0 cell, my apologies, a 1 cell building the equator, a 2 cell on the top, a 2 cell on the bottom, and then you put a 3 cell just to fill in the space inside. So let's first do pi2 of S2 S1. So pi1 of S1 is of course Z plus, then you have two cells. So by Whitehead theorem, the fundamental cross module of S2 S1 is the free cross module on the map, on the attaching maps of 2 cells. So it's the free cross module on the map from the set of 2 cells, C1, C2, where C1 attaches along 1, and let's say that C2 also attaches along 1. So that's just what it is. And concretely, this is of course just the map from Z plus Z into Z, sending AB to A plus B with a trivial action. And now we can ask, so how do you go from pi2 of S2 S1 to pi2 of D3 S1? Geometrically is quite evident. So if you attach a 3 cell to the interior of S2, you'll make C1 and C2 homotopic relative to the boundary S1. So, well, the fundamental cross module is like the one above, but imposing that C1 is equal to C2, and a quick calculation just says this is just the identity map from Z into Z with a trivial action. This is as simple as this. So, but this is like the pattern I'm going to use when I'm going to look at knotted surfaces. If you want to compute the fundamental cross module of a CW complex, you consider the free group on the 1 cells, you consider the free cross module attaching maps of the 2 cells, and then one relation for each 3 cell. And it's more or less like here, but the attaching maps could be more complicated. Right, before I go to knotted surfaces, which was the main aim for today, let me just speak about a certain homotopy invariant, which I called IG. And in order to underpin it a bit more, let me just say that if you have a space X, which is a CW complex, there's of course lots of different CW decompositions you could choose for X, but up to homotopy, the fundamental cross module doesn't depend on the CW decomposition of X, really up to homotopy. And moreover, let's choose X and Y homotopic CW complexes. So pi2 of xx1 doesn't need to be equal to or isomorphic to pi2 of y1, but they are almost isomorphic in the sense that I can find non-negative integers m and n such that the left-hand side cross module becomes isomorphic to the left-hand side cross module by doing enough free products with the fundamental cross module of the disk, which actually also gives a proof that pi2 of a CW complex relative to the one skeleton is actually a homotopy invariant. And this gives rise to a very nice homotopy invariant, which can easily be calculated for complements of knotted surfaces. And so let's grab a finite cross module, G, let X be a reduced CW complex, and let's consider this quantity. So it's the number of representations of the fundamental cross module of X relative to X1 in G, so the cardinality of the set of homomorphisms of pi2 of X1 all the way to G. But recall that this person here is only defined up to homotopy. So in order to take away this difference, I need to consider the following normalizing factor, which is 1 over cardinality of E, number of one cells of X. And what you get does not depend on the chosen CW decomposition of X and is also a homotopy invariant of X. And it has actually a beautiful interpretation. So what is this IG of X? So every cross module has a space associated to it, which is called the classifying space of a cross module, which is a generalization of the classifying space of a group. And is a particular case of the classifying space of a simplicial group. So what do you do? So you have your space X, you consider the space of maps from X into BG and choose one representative of each connected component. And then you need to actually consider the fine normalization. So it's not just the number of homotopy classes of maps from the space into the classifying space of the cross module. You need to normalize with pi1 of the space of maps from X to BG relative to F. And I just realized there is a typo here because this is, I shouldn't have here the space of maps from X into BG. I should have put here the space of pointed maps from X into BG. Okay, by the way, another way to speak about this quantity here, this is what Quinn calls the homotopy cardinality of the space of functions from X into the classifying space of the cross module G. Right, I think I have enough to start speaking about knotted surfaces. Yes, let me now show you a way to calculate this fundamental cross module of pi2 relative to the one skeleton for the complement of a certain knotted surface. So let sigma subset S4 be a knotted surface. Again, any genus, any number of components. I think this time I'm going to take it orientable. And I'm going to suppose that the projection on the t variable defines a Morse function in sigma. Yes, so that's what it is. So this is your knotted surface sigma, and I'm going to assume that the projection on the t variable is a Morse function. And to simplify my discussion now, I'm going to suppose that the critical points of the Morse function appear in increasing order as t increases. And I'm also going to consider this space sigma t, which is called just a slice of sigma at the point t, and I'm going to call it the still of sigma at t. Okay, right. So if I have such a presentation of a knotted surface, I can more or less easily figure out the handle decomposition, i.e. a fat CW decomposition of the complement of it. And when you learn about Morse theory, you learn that if you consider the inverse image, if you consider the stills sigma t, the topology of the stills can only change when one passes the critical point of the Morse function. And it's actually the same thing happens to the complement. So if you look at the complement of the knotted surface, the topology of the complement only changes when I pass a critical point of the Morse function. And when I pass a minimal point of the Morse function, I need to attach one handle to the complement. If I pass a saddle point of the Morse function, I should attach a two handle to the complement. And if I pass a maximal point of the Morse function, the topology of the complement changes by attaching a three handle. So this is exactly what I have here. So minimal point in sigma yields a one handle of the complement. Hence, if you want to compute the fundamental cross model, it gives you a free generator of pi1 of m1. And a saddle point in sigma yields a two handle of the complement. Hence, every saddle point should give a free cross model generator. And each maximal point in sigma will yield a three handle of the complement. Hence, a two relation that must be imposed on pi2 of m2 m1 in order to get pi2 m m1. And what I would like to argue today is that it's actually possible to do this explicitly, and as long as you have the movie of sigma. Right, so in order to explain what movies are, I don't know if Scott already explained it in previous talks of this series. Let me just do a movie for a knotted union sigma of two tori, which is probably the simplest knotted surface you can think about. So as you see, if I cut the surfaces horizontally, so I have all of this still. So first two circles, then four circles, then these two circles merge and give rise to one circle, and then the circle disappears. So let's see what happens. So first, if I cut add nothing, then add two circles. So this circle is this one, this circle is this one. And then there is like a catastrophe here. So a point where the top of this circle, so the top of this circle connects with the bottom of this circle. And this point corresponds to this point, which is a saddle point. And then the two circles split into two. And then you could think, okay, from this point and to this point, nothing happens, but let's not forget that we are in S4. So in between this point and this point, these circles can be doing a lot of things in 3 space. And I'm actually going to assume that in between this point and this point here, this circle here goes inside this circle and then comes out. So I think the movie is more or less written here. So this circle becomes a bit smaller, goes inside this circle and then comes out the other way. And then we're back to where we started, and then, well, then we just undo what we did. And this is actually a knotted surface. It's not the same thing as the trivial disjoint in two tori. And let me explain how to calculate the fundamental cross module of the complement of it. But first I need to explain the algorithm to do it. So let sigma in S4 be an oriented surface. Let's consider Morse conditions as above. And as usual, mi is union of the angles of degree less than or equal to I. And let's first see what we do to minimal points. So an oriented minimal point looks like this. So first we add nothing, and then we have a circle. So a minimal point yields a one angle of the complement of the knotted surface. And hence, we need a free generator of pi1 of m1, and we're going to denote it just by putting a letter next to the circle, and letter means like, okay, a symbol for free generator of the free group. And by the way, that free generator can concretely be defined as if it was the Wirtinger presentation. And as the movie evolved throughout an isotopy, we must actually pay attention to what happens to these generators of pi1 as time passes, because we have relations between generators at different times. For example, we could have a Rademacher 2 move, and I'm sorry if you cannot see the bottom of this thing. So this was at time t1, this was at time t2. And so the generator given by this arc is equal to generator given by this arc here. So these are generators, relation between generators at different times. And if you wanted to know the value of this generator here, well, we just use this formula. This generator here will be x, y, x minus 1. And we are still just looking at a presentation of the fundamental group of actually a four-dimensional handle body, just one cells. Right, so let's now speak about what happens at saddle points. So what is an oriented saddle point? And actually that's the point where orientations actually help a bit. So this is how an oriented saddle point looks like. So this is before and this is after. And now there is a little extra information that you need to add, because when passing the saddle point, you must add a band, which is kept throughout the movie. And this is the band, okay? Instead of just forgetting that we had first this and then this, I'm going to add a band. So this band will later bookkeep where the saddle point was made and the attaching region of the corresponding two handle. By the way, the attaching region for the corresponding two handle when I attach a two cell is exactly this circle around the band. Right, so each band gives a free cross model generator by Whitehead theorem. And so I'm going to represent it like this. So this is the generators before, this is the generators after. So the element of pi1 here is the same as the element of pi1 here, but here I have an element of relative pi2. And if I want, and don't forget that cross modules are free on maps, so I always must say how these two handles attach, and the handle corresponding to this band here will in this case attach along x minus 1 y. And bands are to be kept and involved throughout the rest of the movie. We really must know exactly where we attach the two handles. We must not forget about this information. And I'm going to tell you later, and that's why we need to keep these bands throughout the rest of the movie. It's a bit of redundant information that you need to put on movies, because movies of knotted surfaces don't have this band. They don't care about where the handle, where the attachment of two handles was made. But for us to be able to calculate the fundamental cross model of the complement, you must really remember where you did these attachments of two handles. Right. Maximal point. So what is an oriented maximal point? Something like this. First I have a circle and then I have nothing. But don't forget that we added some extra information to the movies, which were these bands which we added at the saddle points. So before the maximal point, the configuration would look something like this. And actually, that's now you can see the usefulness of actually keeping these bands. And the two relations that I would put when I attach the triangle corresponding to this maximal point would look like below. Okay, by the way, if the generator of pi2 here was E, the generator corresponding to this side is x minus 1 acting on E. Okay, there's actually a higher order Wertinger calculus going on here, but let me just say what the two relations we would get are. So you choose any initial point in the circle and you just literally go around the circle and tell me what you found. So first you have E, then you have F, and by the way, notice that these bands are oriented, because without this orientation I wouldn't know how they would define elements of relative pi2. Anyway, the two relation would be this one. So E times F, x minus 1 acting on E minus 1 because it's pointing the other way, and these ones here you just do nothing because they're actually pointing to the interior. Right, so this is the calculus. So let's just give one example, which is this very simple example of a knotted surface I've shown before. So as I said, so this is like a knotted union of two tori, where this circle here goes inside this circle, then comes out in between this point and this point. Okay, this little circle goes inside this middle circle, then comes out. Right, so first you had nothing, and then we attach two circles, and each of these circles will give a generator of pi1. So we have two generators of pi1, let's call them x and y. And now each of these circles splits into two. And in doing so, I need to attach two handles. So I have two saddle points, one here and one here. let the saddle point be labeled by E, and this saddle point be labeled by F. Right, so X and Y give us generators of pi1. E and F gives us free generators of pi2 as a cross module, and because they're generated as a cross module, you must specify their touching maps. A partial of E is equal to 1, and partial of F is equal to 1, which is actually quite clear if you just, well, if you look at some figures. Right, and now let's see what happens after. So the next stage of the movie is this circle here, going inside the circle here and then coming out. So let's see what happens. Something like this happens. So this circle goes inside and comes out. So all of these generators of pi1 get acted by X, actually in this case conjugated, and this generator of pi2 gets acted on by X. Right, and this is not the end of the story or movie or film. Now this circle got to merge, and this circle has got to merge, and here is the merging. So in doing this merging of this circle, I need to add a new saddle point. I think it's here. I need to add a new saddle point here. I think it's here. Right, so let's just now see where all of these guys attach. So G attach along the trivial group element. H is more complicated. It attaches around x, y, x minus 1, y minus 1. Notice that this bit here is called in a different way in comparison to this. And now let's see the two relations. Let's start to the two relations determined by this one. So what is it? So it would be E, then E minus 1, x acting on F. F, I mean counting signs. And now let's see the relation that you get here is simply F, x acting on F. So the relation will be this one. By the way, this is a bit like the Wertinger presentation. So when you attach the three handles, one of the relations comes for free. So this relation here is actually a consequence of this relation, because we actually only need to, so one of the three handles you attach will actually be cancelled by a four handle. So one of the three handles is actually not needed as far as computing the fundamental cross module is concerned. Okay, so this is an example.
Wait, we're still at two handles. So these, you still need all four of these relations here. You haven't put two handles on that.
Wait a second. It's these relations here. There are two types of relations here. So these are not really relations. These are just attaching maps of cross.
Okay.
My apologies. They would actually induce relation at the level of pi1. Is these last two relations should be separate because they're completely different from the others. My apologies for my bad slides. One of them comes for free. And actually you can see one of them comes for free because they're actually the same. And the reason is that one of the three handles is superfluous because it's going to be cancelled by a four handle. It's a bit reason, Wertinger presentation, one of the relations come for free.
Okay, I wasn't seeing those last two relations as three handles. Now I see why you're saying that.
Yeah, my apologies. Yes, thanks for interrupting me. I tend to go a bit faster than I should. And so concretely, this is the fundamental cross module of complement of that knotted surface. So you look at the free group on X and Y, then you have four cross module generators. Most of them attached along the trivial group element, H attached along the commutator, and this is the only two relations. So F is equal to X acting on F. So in this particular case, pi1 would be easy to compute. So this is just the free abelian group on X and Y. So if you want to calculate pi2, you actually need to calculate the kernel of the map from relative pi2 into pi1, which is normally a very hard task. In this particular case, this is possible. And so pi2 of M is just, pi2 of the complement is just this space here. So you consider the algebra of Laurent polynomials on X and Y, then consider the module with three generators, E, F, and G, and then just impose this relation, F is equal to X acting on F. Right, so remember that there was a counting invariant associated to all of this cross module stuff. So if you had a finite cross module, could consider that invariant IG, which essentially is counting the number of maps from the fundamental cross module into this other cross module. And concretely, if we use a cross module which is finite and such that partial V is trivial, then that's the explicit value of IG of M. Right, let me just do maybe one more example, and I promise I'll speak today about welded knots and biquangles. Right, let's just do the span Hopf-Link, which is like a knotted T2 disjoint union T2. And let me just look at the final stage of everything. So let's start coloring things. So I'm going to go a bit faster. So we have 2 1 handles, you have 4 2 handles, and 2 3 handles. So you have handles E, F that attach trivially. Where are they? So this one attaches trivially, and this one attaches trivially because this side is the same as this side. Then you have 2 1 handles that don't really attach trivially. They both attach along commutators. And right, and now we have a 2 relation for each of these 3 handles I still need to attach, and the way to do it. And very sorry if you cannot see the bottom of the page now, but it's essentially what says that F times X acting on F minus 1 times, I'm sorry, I started in a different place. Yeah, Y acting on E times E minus 1 times X acting on F minus 1 times F is equal to 1. But this is the algorithm. It's really as simple as this. And like I said, I just need one of the relations. I just don't need the 2. And with this, you could easily compute the fundamental cross module of the complement of the Hopf-Link, of the span Hopf-Link, well, relative to a certain one skeleton, and it's written down here. So free group on 2 generators, X and Y, 4 cross module generators, 2 of them attaching trivially, the other 2 attaching along the commutators. And this is the only 2 relation we have. So pi1 of M is again the free Abelian group on X and Y, and pi2 of M is considerably different. So it's the quotient of the module over the algebra of Laurent polynomials on X and Y with base E, F, and M, considering this relation here. And by the way, we could again consider this counting invariant, and the counting invariant would be actually quite different. In fact, this counting invariant IG can, in a lot of cases, because don't forget this IG depends on the choice of a finite cross module, can actually distinguish the span Hopf-Link from the knotted surface above. By the way, I singled out these 2 knotted surfaces because they both have the same fundamental group. The fundamental group is Z times Z. So it's actually an example of 2 knotted surfaces with the same pi1 of the complement, but different pi2 if considered as pi1 modules. Okay, I'm always looking at pi2 as a pi1 module. Okay, and I did not compute the Poshnikov invariant or the K invariant of these 2 examples, maybe for laziness, but fundamental cross module, which is here, says everything about homotopy 2 type. So from the point of view of knowing what homotopy 2 type of the complement of these knotted surfaces, we don't really need to compute pi1, pi2, or the K invariant. Right, so let me just speak about a few more results about discounting invariance. So recall that if you have a finite cross module, we can define this homotopy invariant, this IG of M, which computes the number of homomorphisms from the relative pi2 of M relative to one skeleton into the finite cross module G, and then it's normalized by cardinality of E times D1 of M1, i.e. the number of 1 cells if M only has 1 0 cell. So first result is that this map that sends sigma to IG of S4 set minus sigma is able to separate between pairs of Riemann knotted surface with different knot groups if you vary G. And an example is actually the example just above, the span Hopf-Link and the other knotted surface, which I don't know which name it has. And I promised I would go to Quandles today, in this case by Quandles. I'm going to recall Shinsato's tube map, which is this map T from welded links to knotted tori, which I believe Roger spoke about a few weeks ago. But if you want to reference this reference here, Shinsato, virtual knot representation of ribbon torus knots. And what? So there's this theorem, if E mapping to G is a finite cross module, and the boundary map is trivial. If the boundary map is trivial, things become a lot simpler because the two cells really don't, the two cells are milder to look at computationally. And this welded knot invariant that sends K to IG of S4 minus a tube of K can actually be calculated from a certain biquandle, which is this biquandle here, which I'm sure it has appeared and maybe discovered somewhere else, but it's a biquandle that really computes this counting invariant number of maps from the fundamental cross module, the complement into this finite cross module. By the way, this only works if partial is trivial. And by the way, I should say that there is actually a co-author going on here, because the discovery of this biquandle was started a few weeks ago, not weeks, a lot of years ago, when the visit of Louis Kaufman to Lisbon, which actually asked me, so what can you compute this cross model invariant for complements of the tubes by using by using Shinsato's map? It turned out to actually, yeah, you can actually do it, and actually the proof of this result that this counting invariant can be calculated from this biquandle is essentially in this paper, invariance of welded vertical knots by cross model invariance of knotted surfaces, which is already a note paper, 12 years old. And by the way, I'm saying proof is essentially there because it still model a couple of details which I actually never wrote down. And let me speak a bit more about this biquandle below. Again, it depends on A, which is a abelian group acted on by a group. And okay, this is the way this abelian G model, this biquandle looks like. And this has since been revisited in two different angles. So this is paper with Alex Bullivan and Paul Martin, and actually we discovered the connection of this biquandle to modeling loop particles in discrete triples non-dimensional higher gauge theory. It's a recent paper. And even more recently, Celeste Damiani, Paul Martin, I just wrote a paper which is a lifting of Artin representation to loop rate groups, and Artin's representation only looks at pi1 of the complement, but this lifting actually looks at pi2 of the complement of a disjoint union of circles and the action of pi1 on pi2. And I should probably stop here because it's exactly 55 minutes since I started. Any question?
I have a question.
Yes.
Have you looked at non-orientable surface embeddings like RP2 or the Klein bottle in S4?
Not really. They become a bit messier because they attach in a non-orientable way. So like this calculus would probably be considerably more complicated because if you have oriented surfaces, you know that you can always have orientations on the stills at each moment. But if you have projective planes and Klein bottles, this disappears. So I'm assuming it will be possible, but slightly messier.
Okay. Any intuition as to what the K invariant is saying? Are there examples of knots with this everything the same except the K invariant is different?
There are examples. I've never looked at them, and there's actually one of the papers I actually put in the very beginning of this talk. which is Plotnik Sucio. I never know how to pronounce his name, which is called K-invariance of knotted two spheres, which I should probably get to. And they give at least one example of a pair of knots with the same pi1, pi2 action of pi1 and pi2, but different K-invariance. It's a very tricky paper, and I have never completely understood why it works. This paper here, Plotnik Sucio, K-invariance of knotted two spheres. And yes, but I'm assuming that you should probably be able to tell apart different knotted surfaces, different knotted surfaces with the same, with different, well, same pi1, same pi2, but different K-invariances by looking at this counting invariance, but I've never done the calculations for that.
It's good to see another fan of J.H.C. Whitehead. His papers are like reading an Agatha Christie novel. He just gives you barely enough clues to understand what's going on there.
Yes, and then
Great, very nice work. Very nice work.
yes, I mean there's some reinterpretation of Whitehead's work in this work of Brown and Higgins, which is actually what I actually understood enough to be able to write these things.
So following up on Sam's question, it might be worthwhile to take the connected sum of a standard projected plane and a 3-twist spun trefoil and see if that was different than standard projected plane with a 0 spun trefoil. So if you could find an invariant that would distinguish them, that would be very, very, very interesting.
Oh, I'd like to see that. But are they different knotted surfaces, or?
We don't know. And I guess I'm curious if the K invariant is related to the quantal cocycle invariant.
That I don't know. I should probably ask Samuel the Monaco, because I looked at cross modules, not quite at the K invariant.
I don't know at this time, no. Good problem, good problem.
Yeah, thank you. I'll have a look at it.
I suppose you could work out the invariant just from the of a welded knot, just from its appearance as a welded knot. I mean,
well, you have a biquandle that lets
Yeah.
you. Most of the details at some point should be written, which is the usual biquandle invariant. In fact, those two examples of a knotted surface that I gave at in, they're like secretly tubes of knots. One is the tube of the Hopflink, and the other one is a tube of Hopflink, where one of the crossings is virtualized.
Sure. Yeah. Yeah. Well, it's a very interesting talk. Thank you very much.
Thank you.
Very nice, very nice.
Yeah.
Thank you.
Any more questions?
Be sure to send us a copy of your slideshow.
Oh yes, I'd like a copy of that.
Yes, I like that. And a copy of your paper.
I will put it in the Dropbox.
Yes.
Oh,
So
yeah.
let me just be adamant. I mean, this biquandle was discovered a long time ago in Lisbon when Luis was visiting. It's quite interesting.
So, okay, if there are no more questions, Sam, do you want to say anything?
Next week, I'm not speaking on 2 knots, but I am speaking on mosaic knots and quantum knots. That's what I'm talking about. So it's a totally different subject. This must be said. You can relate knots to quantum mechanics. And so I'll be talking about that a little bit too.
Okay.
I'll send-
Well, we'll
I'll send
look
you the
forward to it.
slides early.
Okay, thanks. Yeah. Okay,
Oh,
well, if
What's happening on Friday?
I'm talking.
That's
Oh,
Oh,
this
I
week.
thought you said next week.
It's this week.
it's this week.
I'm talking about quantum knots on Friday and mosaics.
That's the trouble with lockdown. You lose sense of time. Okay. So, well, thanks everybody again, and I'll stop the recording and
Okay.
see you all.
Ciao.
Ciao.
Bye-bye.